Hello everyone. Now we reached chapter 10. The topic is acid-base titrations. So far, we have learned the principles of acid-base chemistry. Okay? And we also considered polyprotic acid-base um, reactions. Yeah? And also we considered how to prepare buffers, okay, from acid-base reactions. Okay, now let's consider the practical aspects of acid-base chemistry. That is acid-base titrations. Okay, somehow it is very straightforward, okay? But it is very practical. So the front cover of this chapter concerns with acid-base titration of a protein. As you know, protein has many amino acids. Okay, and uh, many of amino acids have substituent groups. That is um, protonatable. Okay, let's consider the ribonuclease. This is the protein that um, is made of 124 amino acids. Okay, the function of this enzyme is to cleave RNA into small pieces. Okay, and very surprisingly, um, the, this kind of protein, right, could be studied by acid-base titration. Okay, and it is known that it has um, isoionic point around let's say 9.6 or something like that. Okay, the isoionic point is that when pure, the protein is dissolved, yeah, and then the pH of that pure protein solution, yeah, is the isoionic point, okay, and isoelectric point is very close. Okay, this titration curve, okay, is made starting from this isoionic point, okay, by adding hydroxide, by adding strong base like KOH, okay, or NOH. Yeah. Then the people measured the pH, okay, this part, okay, and from this part when you added strong acid, okay, and then as titration goes on, this pH changes, it decreases, okay. These uh, these are the experimental points, okay. And this line was calculated from pK values of titrable groups of amino acids that are constituents of ribonuclease. Okay, although there are many amino acids, but theoretically it is possible to construct this kind of titration curve using these experimental, okay, these experimental data, okay, and uh, from this curve it is possible to deduce the approximate pKa values for each titrable group, okay, and also this curve provides insight into the environment of that amino acid in protein. For example, you see this tyrosine. Okay, tyrosine has this substituent. Okay, and this proton here, this is titrable. Okay, by adding hydroxide ion, and then this proton uh, is removed. Okay, from the amino acid, from this protein, ribonuclease. But when you look up the table 9 uh, dash dash 1, and then you'll see pK values for those substituent groups. Okay, and tyrosine residues have normal pKa, around 10. Okay, but here you see around 10 here, uh, but when this tyrosine residue, this one is um, surrounded, by this protein. This proton, yeah, is inaccessible by hydroxide ion. Okay, so when you titrate with strong base, only this proton um, is removed. Okay, so this way it is possible to deduce, yeah, the what the environment of the amino acid in the protein look like. Okay, so theoretical titration curves for enzymes can be calculated from known structure and principle of electrostatistics. But this is rather, very the difficult procedure. Okay? When I look up this paper, this paper was published a long time ago. Yeah, but it is not easy. But in principle, it is possible to theoretically construct, these titration curves considering the protein structure. Right. The point here is that this well-known X-based titration could be applied to study even what the protein like a ribonuclease. Okay. Okay, let's consider the easiest case. Okay, which is the titration of strong base with strong acid, or titration of strong acid with strong base. Okay, this is the most you know it's the easiest case, and our goal is to construct a graph showing how pH changes as titrant is added. Alright? The first step is to write chemical reaction between analyte and titrant. Usually, titration is performed by preparing your analyte solution, and also you have to prepare the titrant of known concentration. Okay, so titration usually is in the burette. Okay, so you add titrant into analyte, drop by drop. Okay, analyte is the known solution, you want to measure. All right, so the reaction between strong acid and strong base is very simple. This is a net reaction. Okay? This proton comes from strong acid, and hydroxide ion comes from the strong base. That's it. That's very simple. Okay, so it makes water, right? So from this simple reaction, you can immediately think that, oh, the equivalence point, at equivalence point the pH must be 7. Yeah, that's right. And let's consider one by one. Here is an example of 50 milliliter of 0.02 molar potassium hydroxide with 0.1 molar HBr, hydrobromic acid. Okay, what is the equilibrium constant for this one? This is a very, very big, such a big, but we can calculate. This is the reverse reaction of water autoprotolysis. Yeah? We know Kw is 10 to minus 14, so this is the reverse reaction, and equilibrium constant for this reaction is 1 over Kw, which is 10 to 14. You see, this is extremely large number. So virtually there is no reverse reaction here. Okay? Uh, when you consider titration curve, it is good to consider three regions. First, before equivalence point, and second, at the equivalence point, and third, after equivalence point. Okay, we divide the titration curve into three parts. Okay, before and at and after the equivalence point. All right. In this case, um, so in order to find out the equivalence point, so we have to must first calculate the equivalence point. That means we have to calculate um, the volume of this strong acid to reach equivalence point. Okay, so um, this is one-to-one reaction. So number of moles of hydroxide ion equals the number of moles of the proton uh, ions. Okay, at equivalence point. So we can very easily calculate. Okay. What is the number of what is the volume of HBr? You know, but number of moles is the volume multiplied by concentration. Okay, and it is equal to the moles of hydroxide ion. Okay, so we can set up this equation. All right, VE is the volume at the equivalence point, and uh, it is multiplied by the concentration and is equal to the volume 50 ml times 0.02 molar. Okay, so we can very easily calculate the volume at the equivalence point, which is 10 milliliters. All right. And let's consider the region 1, the before the equivalence point. Okay, since we know already VE is 10 ml, so now we consider 3 ml of HBr is added. Okay, and what is the hydroxide concentration? Since the HBr volume doesn't reach the equivalence point, in solution there are still excess hydroxide ion concentration. So we can calculate the concentration of hydroxide ion. Okay, yeah, let's follow this equation. This first part, okay, is the fraction of OH minus remaining, and second part is initial concentration of hydroxide ion. Then third part is the dilution factor. Okay, but I don't want to uh, I don't want you to follow this way, but please listen to my explanation. Okay, let's see. Since 3 ml of HBr was added, and also 3 ml of potassium hydroxide is reacted with HBr, and what is the remaining volume of potassium hydroxide? Yes, 7. Okay, 7 ml, and 7 ml times original concentration. This one 0.0. This one gives the moles of hydroxide remaining in solution after adding this volume of HBr. But since you added HBr, so total volume increased. Okay, so you divide by what? 50 plus 3. Okay, that way you can easily calculate hydroxide ion concentration. Now it is 0.0132 molar. Okay, this is the hydroxide ion concentration, and proton ion concentration is given by this equation, and we get this number. So pH will be 12.12. Okay, by the way, what is the initial pH here? So initial hydroxide ion concentration is 0.02. Yeah, first you calculate hydroxide the pOH, or you can calculate here proton concentration. In this case, we use 0.02, yeah, for the initial pH calculation, and it will be greater than 12.12. Okay, and the second region is at the equivalence point, right? The net reaction is this one, yeah. So you don't have to calculate anything, yeah. And proton concentration and hydroxide ion concentration is the same. So pH is 7.00. All right, very simple. And third region is after the equivalence point. Okay, let's consider just you added 10.5 ml added, you know. So what's the excess volume of HBr? Yeah, yes, right, 0.5 ml. Okay, this was added excess. Okay, and then what's the mole of proton? Excess mole of proton concentration, protons. Okay, yeah, 0.5 times what? What was the original HBr concentration, which is 0.1. Okay, so you multiply 0.5 times this concentration, and since volume was increased, initial volume was 50 ml, now you added 10.5 ml, so total volume is 50 plus 10.5, which is 60.5. Okay, and then you will get proton concentration of 8.26 times 10 to minus 4 molar. So pH is 3.08. Wow. You see, just adding 0.5 ml more, after the equivalence point, pH decreased from 7 to 3.08. Okay? That's the characteristic of uh, titrations between a strong acid and strong base. All right. So we can construct titration curve like that. Okay, here, this is the titration curve of strong base with a strong acid. Okay, now we start a very high pH. Okay, and when you add strong acid, pH at first slowly decrease, okay, slowly decreases, and then near the equivalence point, pH, abruptly mm, what changes. It abruptly decreased, you know, very rapidly, and then when you add more and more strong acid, and then now uh, it uh, it goes like that. Okay, yeah. So pH 7. This is the equivalence point. Okay. Another way to find the equivalence point is that when you differentiate this curve, and it will give you the peak shape. Okay, and the peak position is the equivalence point. And if you differentiate one more time, second differentiation, and then you can find 0 point. Okay, but I would say that differentiation increases noise. Okay, and second differentiation increase much noise. Okay, so in order to apply this technique, your titration curve must be very smooth. Right. Yeah, here is the this table tells that the calculation of titration curve for this one, yeah, and the initial pH, which means that when no HBr was added, pH is 12.30, and then as you add more and more strong acid, then pH decreases, and then abruptly, okay, um, it falls down. Okay, yeah, like that. This is region 1. This is at the equivalence point. There's region 2, and after the equivalence point, that's the region 3. Okay, this is the simplest case and very easy to understand.